So you'll have a notion of where all the wireless hardware fits into our physical wired network, and then that's obviously a whole other separate set of issues. So stop me anytime if you have any questions. I think we've got enough material, but there's time definitely to take detours if we need to. So specifically, as far as the wired network goes, we'll talk about the physical and logical network layout. And in talking about that, we'll cover EIGRP and BGP. Those are routing protocols, the two that we primarily use. We'll talk about spanning tree, which is the protocol for managing loops and providing redundancy on the layer 2 side of the network. We'll talk about routing versus switching, again, focusing on where it's layer 2 versus layer 3 and defining those two. Essentially, routing is layer 3, switching is layer 2. We'll talk about bandwidth utilization. This is a major issue right now because we're using a lot of it. And figuring out how to manage that is really tricky. So we're putting a lot of time and energy into figuring out how to stay ahead of it because we're always just about out. And that being one of the biggest, but then we'll talk about some of the future and ongoing challenges we face on the core network and the wired network. And then after this, we'll get into wireless. Anybody have a particular interest in anything in here? Or? All right. So here is the physical layout of the core network. Have you guys seen this before? In any other presentations? Okay. So let me put us on the map. We're down here hanging off the STS core 6500. Every one of these squares here is a 6509 Cisco switch. We actually have no pure routers in the network at all. Somewhere in the last 10 years, switches started coming out with layer 3 capabilities, meaning switches could route. And so it became feasible to use a 6509 where you would have used a router before. The advantage of that is this thing can function as a switch, it can function as a router. So backing up just a second, I don't want to bore you with stuff you already know, but making a distinction between the two is important as we get into the details of the design. So layer 2 is switches, right? Layer 2 is a single broadcast domain. So any device that's on the network, when it wants to get out, if it wants to communicate, it's going to look at two things that you configure to get from DHCP. It looks at the IP address and it looks at the mask, right? So if it looks at its own IP address and it looks at its own mask and it looks at the destination, it can figure out whether that destination's on the same network or on a different network somewhere else. Everyone with me so far? Okay, so if it's on the same network, that's going to be the same layer 2 environment. So it's going to send out an ARP request. That's a broadcast. That broadcast is going to go all the way up until it runs into a layer 3 or a routed interface. So hanging off of STS, we might have 10 switches off of one interface. When somebody plugs into one of those switches and they try to browse to a website, an ARP request goes out trying to find the destination. Now, if the destination is remote, right, it can't get there on the switch network, so it has to go to what? Default gateway, right? There must be there. So instead of issuing an ARP request for the destination, it issues an ARP request for the layer 3 gateway. So that's the layer 2 situation. We've got all these switches. They're all in the same broadcast domain. When that ARP broadcast goes out looking for either the destination or for the default gateway, it floods through every single port on all those switches. All right, so ideally, if we've got 10 switches hanging off that interface, we'd like to provide some sort of redundancy, right? We'd like there to be some kind of fail-safe, so if one of those links fails, there's an alternate path by which data can get through. What's the problem with that in a layer 2 situation? Loops, right? If you, let me use the whiteboard over here. So let's say hanging off that router. I need to make it bigger. All the S's are switches, the R's are router. And down here's my workstation sitting right here. Okay, so I'm browsing to Google. Google obviously isn't on the local network. There's no servers here, so I'm going to be ARPing for my default gateway, which sits up here on this router. If I don't have some kind of mechanism in place to prevent loops, what are these switches going to do? This switch is going to receive that ARP broadcast, and it's going to forward it out this port and this port. Okay, so in a layer 2 situation, what switches do that's really important, over and above what hubs used to do, is switches learn where MAC addresses are, right? Switches aren't as smart as routers, but they're smart enough to look at the layer 2 header, to look at the Ethernet header on the packet that they receive, and it's going to look at the source MAC address. So when this guy sends out his ARP request, it's got to fill in that layer 2 header with a source MAC address. that switch is going to look at that, and it's going to enter it into its CAN table. So it's going to put a little entry in its table that says, that MAC address is off of this port, and it's going to remember that. All right, so that broadcast gets forward. Remember, the layer 2 header hasn't changed, so that source Ethernet address is still the same as it was when it left this workstation. So now these two switches receive it, right? What do? They say, all right, so let's say this guy's MAC address is AA. Obviously that's not legit, but it saves a lot of writing. So AA is on this interface, AA is on this interface, and it's going to forward the broadcast along. Well, you come to a point before too long where this guy's forwarding the broadcast back here. What's this switch do? Oh, wait a minute, AA just moved. Let me just take care of that. I'm going to delete it over here. Now it's over here. It's fine with that, and it forwards the packet out. Well, what happens very quickly, and bear in mind, inside that layer 2 header, inside the Ethernet header, there is no time to live field. The switch doesn't receive that frame and say, oh, I've seen this before. It receives that frame every time like it's the first time it ever saw it. Right? So those frames never die. They just keep getting forwarded around and around and around forever. We were trying to test 10 gig blades over some distance. So we were trying to figure out how we could fill it up when we didn't have anything that had more than a gig card in it. We didn't want to stack up 10 gig cards on both sides and try to generate that kind of traffic. So we intentionally created a loop. We created a situation just like this, turned spanning tree off, and just started to ping to the broadcast address. We could generate 7, 8 gig of traffic just with that ping looping around. Just a ping to the broadcast address. Because all those frames just keep going around and around and around. They never stop. So this is where spanning tree comes in. All right? Everyone with me so far? Any questions? All right. So spanning tree is going to be a very conservative approach to solve this problem. Spanning tree says loops are bad. I'm going to make sure we don't have any loops. So it's going to take one of these and it's going to break it. Problem solved. Now, I mean, it's not a great solution because I can't load balance. That link's dead right now. But spanning tree will make sure the loop is gone. And it'll also send BPDUs or hellos back and forth between these switches so it can detect if, oh, now that link failed, this link needs to come back up. All right? So that's layer 2. The broadcast domain is not, it's a continuous broadcast domain. So that broadcast packet floods through all those switches. That's what layer 2 means, switched. Same broadcast domain. Spanning tree is the way we make sure that loops don't kill our broadcast domain. Something else I wanted to say. So the issues with spanning tree are it's number one, it is conservative. So if you want to load balance, it's not terribly easy to do. There's tricks. I mean, spanning tree definitely gets more advanced in this. So you can work it out to where you can balance traffic, but it's not easy. Second thing is it doesn't fail over that fast. We use legacy spanning tree right now, which is the original release of spanning tree, and we can never fail over faster than 30 seconds. And in the worst case scenario, it'll take us 50 seconds to fail over. So we got redundancy, but if you're in the middle of a voice over IP call, yeah, you're going to know it, right? I mean, it's clearly 50 seconds is well past whatever limit that application will be able to tolerate. We could move to rapid spanning tree, and we want to move to rapid spanning tree. We just need to make sure that we don't cause outage. And certain areas of the network are really sensitive to outages. So when we make that change, there'll be 5 minutes where things get a little dicey. And we need to make sure everyone's prepared for that and willing to accept it. But assuming we were ever to convert to rapid spanning tree, we could fail over, theoretically, less than 1 second, certainly less than 2 or 3. The reason that rapid spanning tree is better, in brief, is legacy spanning tree, it picks a root switch, and that root switch just keeps sending out BPDUs, and everybody else just regenerates them. Rapid spanning tree works more like a routing protocol. All the switches actually handshake with each other and talk to each other. So anybody can detect a failure, and it gets dealt with more quickly. All right, so back to this up here. We didn't really get even too far into our diagram. The reason it's relevant to talk about that now is this is where all the dorms hang off. This is where all the South 40 wireless hangs off. So a lot of the networks that you and all of the users you support down here use hang off of this switch. The layer 2 network actually doesn't terminate at that switch. The layer 2 network extends through a packet shaper up to a firewall services module on the, well, I got on right here. This is a lot of data. It's the signal port. Okay? So when you issue that ARP request, when someone in one of these dorms browses for an internet site and is looking for its default gateway is up here. So that broadcast is forwarded all the way up. We took a stab at trying to fix that this summer. I say fix. We don't want it that way. We want the layer 3 interface to terminate here. for a lot of reasons. One being that if you're browsing, if you're pinging from one dorm to another, does it make sense to have it work its way all the way back to here, then all the way up, all the way back, and back down? It doesn't. We have to have the packet shaper jerry-rigged to ignore that traffic. And we think we've got that right, but it's not the best use. We shouldn't have to configure the packet shaper to ignore traffic that's going to come right back again. We should just make sure the traffic never goes that way to begin with. I won't go into it now, but if you're curious as to what the issues are with making that conversion, if there's time at the end, or if you're interested afterwards, let me know. I can tell you exactly why it's more difficult to do than we initially thought. Okay, so going up here then, we've got our core, which is comprised of Siegel, Core, Med, and Brookings. That's our three main Danforth core devices. This one sits in Siegel Hall, obviously that one's in Brookings, and this one's down at the med school. These are all connected by fiber that WashU owns or leases. So there's no circuit that we buy. That's a fiber end-to-end circuit. We generate the light, we fill it, we shoot it to the other end. So it's a completely closed WashU circuit. This is another 6509. Technically, we don't count it as a core device. It's the heart of the data center. So all of the Woostel data center resources connect off of that 6509 there. It's redundantly connected with gig interfaces to Brookings and Siegel. And these are also WashU fiber, and they don't take the same path. So where you have redundant connections, they do not take the same path. They're separate runs. And that actually has saved us a few times. We've had times where one or the other has been cut and there was no interruption. So that's everything on the Danforth campus and down at the med school. We still have an whole other half of the network here. Those Gigaman clouds, those are circuits that we lease from AT&T. Those aren't fiber that we control. So we purchase a circuit from AT&T. It emulates a point-to-point Ethernet connection. So from our end, it looks like just any other Ethernet connection. We plug the fiber into a port just like any of the others, and at the other end, we see our device. But we have to pay AT&T for that circuit. Nothing interesting happens there. We have the gig link. There's one gigaman that leaves Brookings Hall and terminates downtown where that commodity core is. That's at the data center down at 900 Walden. So that's a key point in St. Louis. All of the major carriers are present there, and frankly, most of the internet in and out of the city goes through there. So that's a single point of failure for us, but it's a single point of failure for a lot of people. We're working on that. AT&T actually has a connection point that's not there, but it's expensive. So working out how to get there and not breaking the budget is the trick. The connection out of the med school doesn't go straight down to 900 Walnut. It goes to another building, 210 Tucker, where we lease one rack there. This is one of the upcoming things we'd like to get rid of because it's an unnecessary hop. What it does for us is we've got one circuit that connects there, and then from 210 Tucker down to 900 Walnut, we have 4 strands of fiber. So we can take that one physical link that we're paying for from AT&T, and we can run 2 logical circuits across it, just separate VLAN. So one VLAN connects through Tucker and goes to commodity. One VLAN connects through Tucker and goes to SLIAC, which I haven't talked about yet. SLIAC and commodity sit in the same rack downtown at 900 Walnut, right on top of each other. This one technically is not a WashU-owned device. WashU manages an internet access consortium called St. Louis Internet Access Consortium. Currently, it's just WashU, SLU, and Donald Danforth Plant Sciences Center. Though we also now connect the Tyson Research Facility there as well. The whole purpose of that entity is to provide access to internet too. So that's why it's on a separate device, because the commodity core, that's a solely WashU's resource, so we can do whatever we want with it. SLIAC, we have to work with our other consortium members to play with that. And then we got a link to Internet 2 and a link to commodity internet. For what it's worth, the commodity internet link currently is Cogent. The Internet 2 link currently is a leased circuit from Cogent that runs to Indianapolis, and that's where we jump onto Internet 2. Internet 2 actually has fiber. The Internet 2 backbone actually comes through St. Louis, but there's no add drop point here, so we can't connect. That would be one of the future possibilities. They would be interested in having us help pay to do that in some way, but that might be convenient. That might be something that would be feasible in the future. That would be a place we can connect. The nearest 2 points where we actually have add drops are Kansas City or Indianapolis. So those are our choices. We have to get to one of those 2 places to connect the internet to. Yes.
I've always been kind of confused by this. What is Internet 2? Like, how is that improving?
Over Internet 1?
Yeah.
Yeah, good. It's actually much simpler than you would think it would be. It's an alternate backbone that anybody can connect to if they work with the Internet 2 rules. It's run out of Indiana University. It is in essence just a giant network that that all these organizations connect to. Once you connect to Internet 2, you can advertise your routes there. So when we connected to Internet 2, we advertise WashU's routes. Any other entity that connects to WashU can advertise their routes into that network. So WashU, all of our public space is 128.252. We connect to Internet 2, we advertise that space. Anybody else who connects to Internet 2, they can see that. Now they can choose to ignore advertisements, they can choose to accept them. For the most part, they accept them because that's the whole point of connecting, to get to as much stuff as you can. So any routes that we learn over Internet 2, we'll connect to over Internet 2. So you don't have to, that's a common misconception, that you have to do something to get onto Internet 2. You don't. If you ever browse to, if you were to leave here and do a trace route from any computer on campus to indiana.edu, you would see SLIAC in the hops, you would see some Internet 2 core routers. It just goes that way, because that's the most specific route. Make sense? So the advantage is, it's a bigger pipe in some places, and there are some services that they make available that, as an organization, we can take advantage of. We can actually peer with other commodity internet providers over Internet 2, which we might do. So what that would do is we would actually learn non-Internet 2 routes across Internet 2. So they've done that, I think, to just encourage people to use it more. Because when you get to the utilization chart, you'll see Internet 2 is not as heavily used as commodity internet. So you could actually just be, you're not connected to anything research related. You're just taking advantage of that circuit as extra bandwidth. The intended use, of course, is that all these research entities would connect to Internet 2. They would all learn each other's network addresses over that, and now we've got a pipe that's dedicated strictly to research where we don't have to compete with P2P, YouTube, Facebook, whatever anybody else is doing. In practice, some of that's on Internet 2 as well. So I guess it's also kind of a platform where they can experiment. They can try new service offerings. These down here is SLU has a connection to us. We don't provide internet access to St. Louis University, but they do connect to SLIAC for Internet 2 access. Donald Danforth, the Plant Sciences Center, actually does connect through SLIAC for both Internet and Internet 2. So we function as sort of a service provider for them. Probably dwell too long on this slide, but anybody have any other questions about this? All right. So I'm not going to dwell too long on this one. Obviously, there's not much you can actually see, but this is the detailed map of the ResNet network. So it gives you some idea of the scale of the thing. It's actually still in progress. Joe Meritek is the guy working on this, and he said he's got 6 buildings left to add, so that's 40 more switches. The trouble is that a lot of the buildings have been done with, there's no chassis in the building. So you might have a building that needs 300 ports, and is being taken care of with however many 24-port switches it takes to provide 300 ports, which would be like 13. Can do that math. So that's not very efficient. So as we replace them, they're on a hardware replacement cycle. They're getting 4,500 chassis, which in one chassis you can support up to 240 some odd ports. It's got redundant power supplies. It's modular, so you can upgrade components individually. It's better. And when that's, as that continues to happen, the switch count will go way down. But one more thing about this, we talk about the size of the layer 2 domain. These are in the same layer 2 domain, right? So that's a big broadcast domain. Now, it's segmented with VLANs, so that makes it a lot better. Every building's in a separate VLAN, so if all these switches are in one building, that's one broadcast domain, but it still spans all the way through here out to. This is the utilization right now. We have a 1 gig connection to Internet 2 and a 1 gig commodity Internet connection. This was actually somewhat of a slow day. We hit 850. On a busy day, we get above 900. Typically, well, during the day, absolutely less than 300 meg of that is from South 40. There's a packet shaper in place that restricts it to that. In the evening, the packet shaper opens up to allow 600. Because obviously the need from the Danforth campus goes way down, so there's no need to just leave that bandwidth sitting there. You can see it peaks late afternoon. We still have people, this is when resident users are starting to pick up and Danforth campus users haven't gone home yet. Settles in for the evening, and then early hours in the morning it starts to fall off to our low, which is 150, 200, which is pretty impressive for 5 in the morning. Other thing that's noteworthy about this slide, notice I got 2 utilization charts up there. This is the commodity link to, let me go back real quick. This is an interesting problem. So we've got 2 1-gig paths to downtown, right? One 1-gig path out of med school. I mean, it splits in Tucker, but it's still a 1-gig pipe right here, so you're never going to fit more than 1 gig on it. And you got a 1-gig pipe out of Brookings, right? And then we've got a 1-gig link to Internet 2 and a 1-gig link to the Internet. So in theory, we're exactly balanced. We're not oversubscribed at all. Except we actually were. Because you can't count on traffic balancing out just right. If as we had it set out originally, the traffic from commodity, as it came back, it would load balance. So half of it would come to med school, half of it would come to Brookings, roughly. From SLEAC, same thing. Half of it goes back to commodity Brookings, some of it comes back to med school. But what if we had a situation where we were using 900 meg on commodity, so roughly 450 going down each path? And then someone at the med school logs on and starts a massive file transfer on Internet 2. That Internet 2 file transfer is going to take its fastest path out, which is directly to SLEAC. So the 450 is balanced, but then med school starts sending 800. This link just got squashed. The routing protocol does not pay attention to link utilization in selecting its path. So if it's got one link that's using almost nothing and one link that's full, the algorithm it uses to determine the best route doesn't factor that in. Now, you might think it would be a good idea for it to, but the problem with that is if you factor that in, then you're going to generate all kinds of load on the routers as they try to keep recalculating routes as the utilization changes. So there's a cost associated with that. So our solution to the problem in the near term was to configure it so that the Internet 2 Internet 2 traffic preferred going through the med school, and the commodity Internet traffic prefers going through Brookings. So if you're a user off the med school, you hit that router and you're going to Google, you go out through Brookings. If you're a user on Brookings and you're going to Internet 2, you come out through med. And the reason we did that is that we could then guarantee that we had a gig all the way out on both paths. If either path fails, then that traffic will fail over. Yeah, and we're 2-to-1 oversubscribed. It's probably going to be a little slow until we get it figured out, but it'll be up. So that's the purpose of showing both graphs, is to show that it's working. Here's utilization on Internet 2. Yes?
Yeah, has this changed in the last year?
Yeah.
And is it just by trial and error that you decide when to open up the bigger packet shaper? Or how did you determine that? Is that just by surveying?
It happens a lot in conversations and working with John. John keeps a really close eye on it, and when he starts to see the complaints going up and it's slowing down, and that's how it happened last year. And the solution was, well, we couldn't really afford to go about 300 meg during the day because we don't have the capacity, but we could do it at night. So that solution was sort of a workaround to get us by a couple of years. Right now, we're doing a lot of work trying to figure out more, I guess, big picture. What are we going to do with bandwidth across the whole network? So we're trying to get a little bit further ahead of it now. The packet shaper that we currently use is maxed out. It won't go any higher. So we need something else. We need to figure out some other way to do this. This is Internet 2. So the traffic on Internet 2 is much more bursty. Here's the tricky part about Internet 2 is commodity Internet, since we've got a whole bunch of people using it, it tends to go up in a predictable way. So you can see, it's going to double every 2 years or whatever. Internet, it can go up from 100 to 800 now. All of a sudden, I started a research project where I need to send huge images back and forth, for an hour every morning between 4 and 5. Yesterday, I wasn't using it at all. Today, I'm using 800 megabyte for that hour. So, for that reason, we have to be careful about using Internet 2 as like an overflow for Internet 1 because we can't predict when it's going to take off and how quickly. Excuse me. Okay, so we shape traffic. We use a packet shaper right now. Reason for this is We only provide 300 meg. The packet shaper sits between the South 40 and the Danforth campus. So we can only provide 300 meg right now without putting the rest of the traffic in jeopardy during the day. The packet shaper's job is to make that happen smoothly. So it uses a little bit of selectivity, but essentially it's trying to make sure that there's fair usage of the scarce resource.
The packet shaper also enforces rules as far as individuals connected to the network. So it tracks and helps make sure that if there's a whole lot of people on the network, everybody gets an equal slice. That's another thing that it helps with.
All right, so as I said, this is one of the things we're working on really heavily right now, is trying to figure out what we're going to do with bandwidth going forward. If we're sitting at 850, 900 meg, we've got a gig connection. Getting up past that gets a little tricky, right? You can't buy a 1.2 gig interface. So it means buying 10 gig cards. Well, you saw our core diagram. It's not just buying a 10 gig card at the edge. We got to get that 10 gig of data all the way down to Walnut. Or we got to find a service provider who can give us a 1.2 gig circuit to us. But typically, if they've got any kind of build out associated with getting that to us, you got to pay them. So that cost is there either way. So adding more bandwidth is, we're at a tricky point, adding more bandwidth. If we do it, it's going to cost money. So the effort now is to figure out what are we doing with all this bandwidth. You know, what's happened. We need to have a clear picture of what's going on. So some challenges with that. The next 3 slides talk about traffic composition. So you can look at flow data. A flow is any unique source, destination, source IP import, destination IP port, and protocol. So if it's UDP coming from this IP address on this port, going to TCP at this IP address on this port, that's a unique flow. And the router actually keeps track of all those flows and exports them to a server, so we can go through and look at all the flows. Not full packet captures. We can't go in and look and see what any of the data is, but we can see how much data was sent in any given flow, how many flows there were. So you can use that to try to figure out what your traffic is. But if you look at it by outside address, this is just the top couple. First off, the heaviest hitter is only getting about 1% of the traffic. And that domain is Limelight. So there's Limelight, there's Akamai, there's all these content distribution networks. We have no idea what this is. There's no way to tell. It could be anybody who's paid Limelight to push their content. Also hosting servers. You could have 100 sites hosted on a single IP address. And there's no way of telling what site someone's hitting. So you have no idea what's going on looking at this. You can look at the inside address. Well, we use an awful lot of network address translation. If you're familiar with this, then you know exactly what that means. If not, then in brief, there's ranges of IP addresses that were never intended to be used on the public internet. So anybody can use them. They won't route outside your network. 10.000 is one. We use 172.16, 17, 18 pretty heavily. You'll see those a lot. Those are private address ranges. Other entities can use those. So we're not allowed to send traffic outside our network sourced from that IP. If we do, it'll get dropped. So we have to translate it. That means when it leaves our network, there's a device in there, a firewall that examines every single packet. And it looks at that source address and it replaces it with a public address. There's some magic that has to happen behind the scenes, right? It has to create a little database, a little entry in a table, so it can keep track of what swaps it made. So when the reply comes back, it can switch it back around again, and you get it none the wiser. That solves a lot of problems. That's the reason IPv4 has lasted as long as it has. Because we can, take 5,000 stations, give them private addresses, and they all share a pool of maybe 50 addresses that have to be publicly used. However, when you want to come in and see what's going on, I want to see where the traffic is coming from. That's coming from wireless controller 7. I can identify a region of the campus, but I have no idea beyond that. So any ResNet network, any wireless network, it's all translated to a PAT address. We can identify how much a given building is using, but we can't see, is that 1 user, is that 10 users, is it 200 users? Is that bandwidth being shared equally? Is it being taken up all by one person? Don't know. So this is what we're trying to work out now. And finally, you can also look at these flows to identify the source and destination port, right? That was part of the flow. So we can look, and that ought to be a good way to tell us, except it's all port 80, right? 74% port 80, and then the remaining portions flash, and then SSL, secure web. Those 3 ports combined are 85% of the traffic. Well, that port 80, there's no way that 74% 0.2% is everybody just browsing websites. There's video, there's P2P, there's all kinds of stuff happening on port 80. Again, we still don't have a good idea of what's going on. So what we're doing now is trying to dig further and get behind these numbers. There's open source tools, there's trying to demo vendor tools, just so we can give a picture of this is what the general utilization of the network is. This is what that bandwidth is using. So we can build the case to add more bandwidth, or if there isn't a case to add more bandwidth, we can work out how to distribute the bandwidth more fairly. Any questions about this? Okay. All right, so this gets to the future and ongoing challenges. Managing bandwidth, I talked a lot about that one. We will, in the near future, we're going to have 10 gig core links. The newest switches we put in the South 40 all have 1 gig access ports. So 1 gig access ports, all piping up to a 1 gig core. You can do the math, it doesn't work out very well. Any one user can fill up that core link. So that's expensive. And not just do you have to buy the cards for all of the routers, but there's firewalls in the path of some devices. And firewalls, they get a lot of money for 10 gig interfaces. And then the firewall itself has to have the processor to deal with that much traffic. So we're figuring that part out now. And then we already talked about commodity internet too. How do you get above a gig, right? We need a 10 gig interface, or we need to figure out how to make it share 2 1 gig interfaces. None of that's as easy as we'd like it to be. New applications, VoIP, video conferencing. Some of this will probably come in a planned way. Departments or broader than that trying to use VoIP. But then there's also individuals setting up little conferences. So departments are on their own, and not in any sort of organized, centralized way. They're buying Polycom MCUs and using them to call around campus. So a Polycom MCU is like just a video phone, so just a big TV, a nice camera, all the protocols built into it, so you can conference. And it's better than a typical one you'd set up on your desktop, and then it'll do fancy stuff. Whoever's talking, it'll put their screen up at the top, and it'll let you schedule events, schedule rooms, so you can put resources on a bridge that everybody calls into. This is coming all right now. And I guess the challenge of it is, if you don't have those applications, this banning tree 30-second failover might be okay, right? I mean, somebody goes to browse for a website, it didn't load, they fumble around, they click refresh a couple times, 30 seconds pass, oh, okay, it's working now. I don't know what that was about, but that's fine. If it's a video conference or a phone call, 911 call, all of a sudden we've got a lot more to worry about. We have to make sure the failover happens faster, happens right. Also brings QoS into the picture. So QoS is quality of service. Ethernet at the layer 2 level and IP at the layer 3 level have fields built into their headers where you can tag packets at a certain priority. So you have to get into the business of figuring out what packets are going to get tagged at what priority. And then you have to set up queues. So you have to say, I'm going to allocate this much bandwidth for things that are tagged like this. And what are you going to do if somebody catches on to how you're tagging packets and they start tagging their stuff is important, So the 911 calls also have my YouTube traffic. So it just creates, it's in the details, right? VoIP is actually not that complicated. I mean, it's just an IP-based application like any other. It's just there's less room for error. The things have to get there right now. They have to get there reliably. 911 is a huge concern because not only does it have to work, but we have to be able to tell where you are. So if you call 911 from a VoIP phone, we have to know which switchboard you're connected to and what room that port is. Virtual labs and cloud computing. So none of this is really out there yet, but the idea is that there's some applications that move a whole bunch of data. It would be nice if you could host all those applications on a central server, host the data on the rack right next door, so in the lab all I have to do is get the screenshots going back and forth. Similar set of concerns as what we saw in VoIP. IPv6, Jason Murray does a really nice presentation on IPv6, and I'm sure you all know kind of what's going on there, but it's the replacement to IPv4, but it's not really built with full backwards compatibility to IPv4, so you have to figure out how and when to start cutting things over to IPv6, and how you're going to maintain compatibility with people who haven't moved out to IPv6. So you basically want to still be able to talk to everybody, while you're making the transition, and that's tricky. It'll also be hard. You know, a lot of devices are going to claim that they support IPv6, but then you get into the details of it, and you know there'll be a little bullet here or there buried in the middle of the documentation that says this feature is not supported on IPv6. The ASA we use in front of the data center, the iOS we have on it right now, would say it's IPv6 compatible. You can write an IPv6 rule set. You can put IPv6 on the interface. It's okay. You're good to go. But there's a little asterisk in the failover section that says active failover doesn't work with IPv6 yet. So that's important. We need that feature. So you don't support IPv6. In that particular case, they have an update that does support it. But that's an example of something that makes it harder. It also, those 128-bit addresses will use more resources in the routers as well. The routers, as the speed of traffic has continued to get faster, routing doesn't work the way it initially does, right? The router doesn't go to a processor, or the packet doesn't, when a packet comes in, a router doesn't go to a processor, have it look through a table, figure out where the destination is, make all the adjustments to the packet and send it out anymore. The router has all kinds of shortcuts, right? It goes through and builds a Ceph table, where it has all those headers pre-built, and where it can do these lookups really quickly. But that means all the traffic that it's seeing, where it's building these tables, it's got to store all of it. Well, now instead of storing a 32-bit IP address, it's got to store a 128-bit IP address. So we're going to start consuming more resources there, and we're trying to figure out exactly what that looks like when we're running both stacks, running 4 and 6 at the same time. How long do we go before that's a problem? And then lifecycle management. This is an endless issue, and it's sort of an endless frustration. I mean, it will be. It's going to go on forever because you can never replace all your infrastructure at once. So you've always got stuff that's not completely the same. But the biggest one that we're looking at now is all those core 6509s. The chassis themselves go end of life in November 2012. So we've got to replace the chassis. A lot of the stuff inside the chassis could go on longer than that, but obviously there's an outage there when you replace the chassis. And so that is a point in time where we'd like to incorporate some of these new things like 10 gig, maybe incorporate more resources for dealing with IPv6. So that necessitates more planning. And as we plan for that, Cisco has a Nexus product line. We do use a variety of vendors, so we have HP switches, 3Com, Cisco. We would definitely consider going with other vendors for the core routing equipment, but Cisco is kind of the easiest path forward for us. I didn't go into many details about EIGRP, but that's our main core routing protocol, and it's Cisco proprietary. So if we were to get any other vendors' routers, we would need to move away from that. So just one more thing to work in. Any questions? That's the end of this part of it.
Okay, I'm Chris Huels. I am also a network engineer at NSS. About a year ago, I acquired the wireless system. So I'm kind of new to it, but yet learning really quickly because there's a lot of people on campus and there's a lot of demands. So here's kind of an overview of what we're going to be doing, what we've got on the South 40. There's 8 controllers down on South 40, 800 access points roughly, give or take. I mean, there's been a lot of new buildings and stuff going this year. 2 radius servers that you guys authenticate through. I believe they all authenticate through Bradford, if I'm not mistaken. The access points for Maru are dumb. They can't function without a controller. They do have some neat functions built into them, but they cannot do anything without the controller. Maru uses virtual cell. It is a single cell architecture. It is where all the access points can look like one access point. So as a user walks, maybe like they're walking through campus, they'll never re-authenticate or reassociate with an access point because they always carry the same DSS ID. And I'll explain that in a little bit. Airtime fairness squeezes as much bandwidth out of wireless protocol as possible. That's a Maru thing that they do. They use something they call tokens, that each client has so many tokens that they use. So like if someone uses 1 megabit and someone else is using 300 megabit, the 1 megabit uses 1 token for their 1 megabit, and the 300 megabit person uses 1 token for their 300 megabit, so they can get one usage of 300 megabit with 1 token, so that the slower peer person doesn't slow the quicker user down. So also in the residential halls, well, we have Bradford for the packet portal, or the Wi-Fi SSID. And Wi-Fi S is the most secure SSID that we have, so we recommend that everybody uses Wi-Fi S. These are the components that we use for Maru. This is the newer standards that we have. If you look on the wall, there's the older 200 series access points. That's probably what you guys are going to see most of on the South 40. These are the newer ones, probably in the new South 40 house or Wool Center, or I don't know if they're called UMRAF. They'll be the newer style access points. Maru also came out with an internal antenna access point this past year. We haven't actually deployed any of those, but we're actually looking at those for maybe like a place like the duck would be a good place for something like that, where they don't want a lot of antennas sticking out and stuff everywhere. Right now we use a controller. It's a 3000 series controller. It actually has a single gigabit connection to it. So if you think about it, right now there's 150 access points that go to that controller. All of the traffic that you guys create, which 100 access points could be, if you think it's 4 users per access point, that's 400 users. Using 54 megabits per person, that's a lot of bandwidth to be pushing through one controller on 1 gigabit interface. Well, these new ones, they have 4 gig, which you can bridge or make as a virtual port. So it's like a 4 gig port going back to the core. So they're a little more robust, and they'll support more users. And they'll also get us ready to move to 802.11n. Any questions?
Just out of curiosity, what are the actual different? I don't really understand the differences between the protocols 802.11a, BG, and all of that. What does that mean?
So BG is okay. So 802.11 runs on the 5 gigahertz channel. 11A is the 5 gigahertz channel. 802.11 BG is a lower frequency, 2.4. So the 5 gigahertz channel won't penetrate walls or get through as much. The lower frequencies, you're going to be able to spread out. You're not going to be able to get the speeds on the lower frequencies that you are on the higher ones, but you can get more of the density. 802.11n, that will run on both 5 gigahertz or 2.4. Does that answer your question? Anybody else? Okay, this is kind of a detailed diagram of the wireless. This is both the Danforth and the South 40. Down here is the South 40. So actually we have 8 controllers down there. I can't tell if there's 8 on there or not. I think there's only 7, but we actually have 8 down there now. As you can see, here's the you can't really see, sorry. It's very small. These are 2 Bradford servers. So as you guys log in, though, you'll be a client out here going through an access point that connects to each controller. You'll authenticate through these Bradford servers, which will then take you through the packet shaper and out to the world. On the Danforth side, there is no packet shaper. You just authenticate through a radius server, and and you're out. Unless you use guest Wi-Fi, then we actually shape guest Wi-Fi on the Danforth campus. Anybody, any questions on that one? I'm trying to go as quick as I can. I know we don't have a whole lot of time. So if you guys have any questions or anything you want me to go over, please feel free to ask. Okay, this is a detailed authentication, how you guys authenticate. It is hard to see as well. It's very cramped in there. So basically, the client associates with the AP and submits authentication through the motor controller, either using Wi-Fi S or Wi-Fi. I think both. I don't know if Wi-Fi. It's been a long time since I logged into Wi-Fi, but I think it goes through the Bradford controller as well. So your credentials will go through the radius, the wind talker, and anchor. If you authenticate successfully, you'll get onto the network. If you don't, you'll be put into the remediation. Any questions on that? Virtual cell versus microcell. So, virtual cell. Let's look at microcell first. So microcell, I think everybody is pretty much aware how that works, right? Is there anybody that does not know microcell? You know? So microcell is like the legacy. No, not legacy. Everybody uses it, except for Murray, of course. It actually is. It uses 3 different channels on the. You got 1, 6, and 11. So you got. Ooh.
It's the black one.
Channel 1, channel 6, channel 11. These should overlap. So basically, if you have a client comes into this, and they're beaconing. So they're going to beacon through here, and they're going to figure that the client's going to decide who is the best channel for them to work on. So each of these access points that are on these different channels are going to send out a different BSSID. Say this has BSSID 1, BSSID 2, BSSID 3. So it's going to see all these different BSSIDs, and it's going to have to pick one of them. So if this client then decides to move over here, say they start walking over here, and then beacons and it starts to pick up channel 11 on this access point. This client decides to move from this access point to this access point, and they have to re-authenticate or reassociate with that access point. So what Maru did was they took and say they got rid of this channel 1 and 11, and they just made everybody channel 6. So now they take away, and now they're only going to broadcast one BSSID. So now it's all going to be BSSID 1. So now it looks like this. So now when that client comes in, and it's beaconing for a network, it's only going to see one network. So no matter where this client goes, it's only going to see one BSSID. Makes it look like one access point. So they can walk around campus and never lose connection. And the way they do that is the controller takes care of all of this. So if they move from this station to this station, the controller is out here making all the decisions for that client. So instead of the client making the decision on what channel or what access point they're going to, the controller actually does that for them. Any questions on?
And is that what
Microcell?
microcell means? That
So microcell was the first one that I did. It was the 1, 6, and 11. So what I did was I went for microcell, and then now this is the single cell, the virtual cell infrastructure.
That's
So it lets you like stream a YouTube video on UFIS while you're walking down the hall of the building and not have drama.
Correct.
Or have to authenticate again.
Yes. Went through that. So we already talked about the clients are no longer responsible for determining the AP to connect to. Still only capable of handling 11 megabits, 54 megabits, or N speeds. Where this is virtual cell does not increase bandwidth, although using Maru technology, it can make it more efficient.
That because you're not having to spend time authenticating.
Yes, and there are ways of, in high dense areas of using all the channels, and it's called using stacking. So say down like an Olin library, where there might be 200-300 people down there at one time. So if you've got a virtual cell, one channel, I mean you've only got 54 meg space, right? You can't cheat that. So what you can do is you take channel 6 and you layer channel 11 and channel 1 all together, and you can use the same. You can still use the same BSSID or SSID, and there's ways that Maru has done or uses to do that, and it's actually a configuration within the controller, and you can still traverse them without losing connectivity. So the more clients, the less total throughput is available. That is true in all cases. Also, there's a YouTube video out there. The CIO or CTO of Maru actually puts it on. It's very good. It's probably pretty similar to what I just showed you. So if you're interested, I suggest checking it out. Any more questions on microcell versus virtual cell? Airtime fairness. So everyone is fighting for precious time, which is always true. Everybody wants the time. Every machine is looking for all the airtime they can get. The overhead of CSMA, CA wastes airtime. That's collision backoff timers. So if someone is trying to use so much bandwidth and someone else is getting on, then this one will back off to let this one have airtime. So that's what that is. It's just so they don't collide. Instead of using bits as the method of determining the amounts you can transfer, Maru uses time. Traditional networks, no matter what the client speed, and end devices only allowed a fixed number of frames per section. If the one client is operating at 1 megabit, the other client is operating at 300 megabits. It will take much longer for the client to transmit its frame, thus donating the time. This is what I was talking about earlier with the token. So it's got like a tokens that allow the person with 300, like an end user, to access the network faster and not be slowed down by maybe a B user. Using time instead of the bits allows faster clients to transfer more frames in time slot, which is what we were just talking about. Using time also helps keep the contention overhead down to limit who can talk to predetermined time slots. Higher density clients uplink and do not overrun single downlink. Airtime fairness operates under these basic principles. Each station gets a token bucket allocated by time, which is again what we were talking about earlier. Slower stations use more tokens to transmit data. That's because they're slower to transmit 1 meg. They're using 1 token every time versus someone that's using 300 megs using only 1 token to transmit 300 megs. A 1 megabit station may take 300 tokens. Again, same thing I've been saying. But how long how do they do it? We don't know. That's what Maru says is in their secret sauce. They don't tell us. We don't know. hard to say. Again, there's the YouTube link below. Yes.
Just, so, I'm sort of confused because I wanted to know, is a token, is that constant? Like, is the value of a token constant? Like, it's always 1 meg? And
No, that's just an example.
It's by time, right? So your token
Yes.
represents a certain amount of time. So if you said slower, that token represents less data. If you said faster, that token represents more data, because you get it for a fixed amount of time.
Correct.
But, so faster clients get more tokens too, as well as bigger tokens?
They get the same amount of tokens.
Same amount of tokens,
Yes.
but their tokens are bigger.
No, the token
They're-
represents time. So if I
Yes.
Oh,
said faster, my
so
token,
smaller tokens.
the token's the same amount of time. If a token represents 1 second, and I can send it 300 megabits per second, I still get it for 1 second, but I just sent it a lot more data.
Exactly.
Okay, so it's a constant.
Yes, it is a
amount of
constant,
time. I did-
but it's in time. It's correct. Anybody else? Questions on airtime fairness? Questions? That was it? So nobody has any questions? Anything else that you're curious about wirelessly? Anything at all? Anything, any concerns? I know there's concerns out there, that's why I asked.
This group understands why there's concerns, so they don't question it.
I know we do have a lot of problems on the residential side of the network, and that's due to a couple different things, probably. There are some older buildings on the campus that it's hard to penetrate the walls with wireless in some of these dorm rooms, like in the suites. There are also coverage, there's probably access point placement problems that were put in from the beginning. They're probably not, it's probably not, the access points probably aren't where they should be in the dorm rooms themselves. So it is a project that we're working on probably this summer, probably these coming summer months, because we can't get into the rooms whenever the students are in there unless they allow us in there, which makes it hard to do like a site survey or something to see where we can put them. So it's something that we're working on. Hopefully next year we'll have all the coverage problems straightened out.
You mentioned that in the newer buildings, there's the newer access point equipment. Will these be replaced with those, and when you put in a new access point in an older building, will it be the newer kind, and does that have a benefit for?
As we move forward, we will be replacing all the older style APs with the newer style access
Mhm.
points, yes.
And does that have a better track record in terms of connectivity?
I think it's all about the same. The newer access points are capable of doing 802.11n, which is faster. So if you log in using Wi-Fi S, you can get up to 300 megabits on your speed, which the older ones are, the max is 54 megabits. So, but they have to be licensed for it. The ones that we're putting on the South 40 today are not licensed for 802.11n, but they can be. I mean, they're upgradable, but it's just a license. Someone has to purchase a license.
So it's a cost factor. Yeah. Anything else? I want to thank John and Chris for coming and giving us a real thorough overview of this. To remind you, there are 2 more STARS training coming up in the next 2 weeks. Next Friday, Brian Allen will be here, also from North Campus, talking about computer